Hello, today we'll be giving our presentation on optimized neural network ALPR systems for microprocessors. I'm Omead.
I'm Zach.
And I'm Hamza.
Okay, we'll begin by discussing the background of our problem, follow that up with describing license plate localization and segmentation, show how data augmentation improved our training, discuss end-to-end system results, look at our lossless network compression, and finally wrap things up with future work. So, to describe our problem, the performance of automated license plate recognition can be greatly improved by the implementation of neural networks. However, neural networks are designed to perform large amounts of computations and store large amounts of memory in order to improve this. So how can we use these networks, reduce them in order to put them on low power microprocessors that can use them at high speeds? Our ALPR pipeline for our neural network pipeline is the following. We will detect the license plate bounding boxes using the first dataset that was provided. We convert and crop those, send them into our second network, which will detect the letters from the license plates, and we put that all together so we have a bounding box with the segmented letters from the license plate.
So once we attempt to prune these to reduce the network size. So essentially what we're doing is we're removing the redundant or the not too important connections on our networks. And so once we do this, we can reduce both the model size and the complexity with the number of computations. And for our networks, we ended up using iterative weight pruning. So essentially we removed all the most important weights little by little, and we continued training on the non-pruned weights repeatedly, doing a few percent at a time. And after we did some pruning, we attempted to use quantization. So basically our original weights are all stored in 32-bit values. But to reduce the complexity and the size, we actually implemented quantization using a codebook. So we took our entire range and split it up into 256 values, which included 0 as a value because we have a lot of pruned weights. And then, using this codebook, we were able to represent each 32-bit number using only 8 bits. And so this gave us a 4 times compression ratio.
On to license plate localization. In order to pick which network to use to localize the license plates, we looked at a survey that was tailored to do this very thing. We found that YOLO has a very high MAP score as well as a high FPS, frames per second, so is able to recognize and localize these images fast. We found that the MAP raised when we raised the image input width to 480 by 480. It raised to 77.8. However, the FPS lowered. Our goal is to raise the FPS back up by pruning and quantizing this network. The YOLO network in general is a single neural network. It predicts bounding boxes and class probabilities directly from full images in one sweep of the image, and it learns very general representations of the objects. It uses an S-bias grid, and each grid it predicts bounding boxes and confidences for those bounding boxes, as well as class probabilities. It combines all of this into the final detected output, which is capable of detecting multiple overlapped images. Our base image classifier for the YOLO network was a MobileNet framework. We chose this because it is a convolutional network that uses depth-wise separable convolutions that keep the architecture lightweight. It was a pre-trained network on the ImageNet 2016 dataset, which we fine-tuned to use the license plate datasets that we were provided. The accuracy measures that we chose were intersection over union, which measures the amount of overlap between the truth and predicted bounding boxes of the license plates, mean average precision, which sweeps over the IOU thresholds and measures the maximum precisions from them, and finally we use an accuracy metric by detecting which images from the which license plates from the images are detected. We pass these into the CRNN. Even if some of the letters are not detected, the CRNN will pick up some of the remaining. For our training results, the YOLO was trained, then pruned and quantized. After pruning and quantization, the model size became 3.3%. The MAP score only lowered slightly, and our training and test accuracy scores actually did outperform the original network.
For our license plate segmentation, once we had the cropped images, we used a CRNN to find out exactly which letters are in the license plate. And basically the network is set up so that it has 7 convolutional layers, some batch norm layers, and then 2 stacked bidirectional RNN layers with some dropout. So when we pruned the CRNN, we mainly ended up pruning only the kernels and the weights for the best results, while we ignored the biases and some other variables. So the results for the accuracy for this originally were about 100. So originally we had a 100% of the size, and then once we pruned to about 68.74% of that original size. So with the quantization, that ended up with about 17% of the size. So the accuracy for this model ended up being very similar. Accuracy for this model ended up being very similar to the original. We actually did a little bit better, going from 90.79% with no errors to 91.53%. Once we pruned to about 51.5% of the original size, we ended up getting a much lower accuracy, so we kept both of these models just to give an indication of how much we can actually prune.
So next, onto the data augmentation. So originally, when we were running the CRNN, we recognized that the accuracy for no mistakes in the entire license plate was actually around 65%, which clearly isn't ideal. So we looked at the number of training set images that we had, and this only really consisted of 1,700 license plates. And so that really wasn't enough. So we thought of doing some data augmentation, and we did some probabilistic transforms. And we ended up with a data set around 31,000 images. And so we just probabilistically do some rotation, shearing, skewing, and Gaussian distortion, and some random distortion. And what we did was essentially look at our train data and recognize that, there were some instances where we had different perspectives. Some of the images were rotated, some of the letters and numbers were occluded, and we tried to essentially yank out all possible information from our given images to kind of give them this transform and extend our data set, because we do have the train data already labeled. So just as an example, this is the original versus some augmented data. At the very top, we have our original license plate. And again, we see that we're able to essentially generate different perspectives and different noise profiles, although the original image was also quite noisy itself. But the perspectives we see here are maybe some skewing to the corners, and also not all of them are very aggressive, like the bottom right is just slightly rotated. So again, this is a probabilistic, so maybe one of these images has more than one of the data augmentations that we mentioned above. And this greatly helped our final result. We were able to get around 91% accuracy with the CRNN on the license plates with no errors at all. And our with 3 errors, we were getting around 100%, I believe. And so that was a great improvement to the network and the performance of it.
So how does incorporating the YOLO network with the CRNN perform? We used a combination of original, pruned, and quantized models for both networks to test this pipeline. The number of inaccurately bounded license plates from the YOLO side is combined with the accuracy measures from CRNN to produce the following table. As you can see in the top left corner, we have the original YOLO network as well as the original CRNN network. Our best accuracy is 88.13%. As the YOLO becomes pruned and quantized, that accuracy lowers to 86.41%. This is in part due to the quantization and accuracy loss on the YOLO side. However, it is made up in part somewhat due to the CRNN side of things. Finally, the CRNN is quantized and lightly pruned to yield a final result of 87.99%, which is only slightly lower than the accuracy of the original networks.
So since we've already quantized and pruned a bit, and we had great performance, we also wanted to see, how we could continue to decrease our network size. So we looked into some lossless compression algorithms, which are actually quite popular from information theory. And the two compression algorithms we ended up using were Huffman coding and Lempel-Ziv-Welsh. And so the essential idea behind this Huffman coding is to generate a dictionary and to give the shortest dictionary code words to the symbols that have the highest frequency. And since we're actually quantizing our weights before, we really do have a small number of a small number of weight numbers, and then we can essentially figure out which ones are used the most and compress our data through using a dictionary that way. And the Huffman code is an optimal prefix code, and it will achieve theoretically the lowest possible expected code length. So that was a great option for that algorithm. And the Lempel-Ziv-Welsh is another algorithm which essentially exploits patterns in the data. So what it will do is start to generate a dictionary again, and it will start to point back to itself. So instead of using the entire data set, it will come and start generating smaller and smaller, it will start generating larger and larger substrings, and it will recursively point to itself. And so in that way, it can greatly compress our data set. And again, just a theoretical nuance is that Lempel-Ziv will actually give you the asymptotically optimal compression ratio for sequences. So these are two lossless compression algorithms, and we did apply them on our kernels. So here we have just a couple of the different patterns that we implemented the algorithms in. We just did a simple Huffman, which got us around 4.7 times compression, a Lempel-Ziv, which got us around 4.8. When we did the Lempel-Ziv, then the Huffman, we were only about 3 times, but the Huffman and then the Lempel-Ziv got 5 times the ratio, and that's essentially what we wanted to go for. And this worked for the YOLO V2. Then moving on for the CRNN, again, we simply applied Huffman Lempel-Ziv, and again, we see that the best way to apply these algorithms is to first do the Huffman code and then apply the Lempel-Ziv algorithm on the result of the Huffman. And so that was a great thing that we had consistency.
For our final results, after doing pruning, quantization, and then applying the Huffman and Lempel-Ziv compression, we found that our YOLO V2 final size ended up being approximately 0.6% of the original size, and the CRNN was only about 6% of the original size. And these are both without much loss in accuracy, and so we can see that we can actually compress the model quite a bit without losing anything.
And so just for future work, although we just did some lossless compression, other things that we can actually try are lossy compression. So just like quantization and pruning, that we essentially are losing information each time we quantize or prune, we can also use some different lossy compression algorithms, which would even more compress our network size, and then we would take that data, those model weights, and we would put them back in the network and see the accuracy and train again, just as we've done time and time again in class with pruning and quantization. And so essentially that's the end of our presentation, and hope you enjoyed it.